I wanted to talk briefly about alkylation of terminal alkynes, basically extending the carbon chain via an SN2 reaction. So this is a very powerful tool that we can use in synthetic problems as a means of extending the chain, changing the shape or the scope of our alkyne, and then we can do some chemistry actually on the alkyne, changing it to a new functional group. So the idea is that these hydrogens here have rather high acidity for a hydrogen attached to a carbon, and so we can use NaNH2, which is the same as NH2 anion. Right, so this is a strong base, and this is the pK here of 25, pK of, well, let's look at what we get first. So then we get an acetylide anion, and we made NH3, right? The pK here is about 35, so we have a 10 pK difference, which means that, excuse me, this side is favored at equilibrium. And now we have an acetylide anion that we can use in basically an SN2 fashion. This is a nucleophile, and if I use a good electrophile, which we know is typically a primary halide or some other primary alkyl group with a good leaving group, I can do an SN2 reaction and end up with 3 more carbons on my alkyne. So it's important that we don't miss carbons. There's one, there's a carbon, right? And right here are the 3 carbons I just added. So when dealing with alkynes, it's actually very easy to lose a carbon, just because we aren't really used to that linear nature of the triple bond. So, you know, do whatever you need to do to keep track of carbons. There are 2 of them right here, of course, because we started with 2 on acetylene, and we added 3 more via our SN2 reaction. So now we have a longer chain alkyne, and as we learned in chapter 10, the alkyne chapter, there's a lot of chemistry we can do with that the alkyne right now. So we could turn it into a ketone or an aldehyde, or add HBr to it, or Br2. And so now we can do more chemistry and then just end up with a more interesting molecule. So let's look at how we might use this in synthesis. Here we might be faced with a reaction that looks like this. Here is acetylene, and here is a much larger alkyne with a lot of extra carbons attached to it. So how do we arrive at that much larger alkyne? Well, we're going to have to do our deprotonation / SN2 reaction. So we use NaNH2. That gets us to the anion. We can add one of the alkyl groups, so let's add this group. You should be able to figure out how many carbons we need to add and what the shape of that group should be. Go ahead and think about that. So this is isobutyl chloride, and that will put on the isobutyl group. And now we have this, which is sort of halfway to our desired product, and we can basically repeat what we just did. NaNH2. Now we have an anion on the other side, and we can add, in this case, the 3 carbon chain that's over there, propyl chloride, and that will get us to the product. And so we could list all of this over the arrow if we want to. Na or NH2 minus, or NaNH2, 2, isopropyl chloride, 3 more NaNH2, and 4 propyl chloride. I said this is isobutyl chloride, I misspoke. And so you can list 4 steps right over the arrow, and that could be how you answer the question, but certainly you're welcome to draw it all out like that. And now, of course, we have a more interesting alkyne. We could do some chemistry on that alkyne if we desired to go further in a synthetic sequence. But what I wanted to point out with this video is that we've made carbon-carbon bonds now, and this is one of the few reactions we know of that allows us to make a C-C bond. And that, as you can see, helps us go from a small, relatively unexciting molecule to something that's a bit more exciting. and certainly we can make that even more exciting by doing chemistry now on the triple bond. So this is alkylation of terminal alkynes, a very powerful synthetic tool that you can use in synthesis problems.